Continuing our discussion of liquid properties, we're going to talk about surface tension and viscosity. Surface tension is the energy to increase the surface area of a liquid, and that is always positive. So what that means is that if you have a liquid, the surface area would be the size of the liquid that's exposed to the air. So if you think about, say, droplets of water, there's some volume, right? There's kind of a pile there, and some of the molecules are on the outside, they're exposed to air, but some molecules are on the inside. So that surface, how much there is, and it is always costs energy to create more surface of a liquid. And so this idea is why we see water form a droplet, right? If you think about if you have a flat surface, water forming a droplet will have less surface area than water being just flat, right? So the same volume of water will go up, and that's in opposition of gravity, right? That those molecules are piled on top of each other because that minimizes surface area. If instead the water droplet was flat, there would be, much lower molecules. You have less piling up, less opposition of gravity, but there'd be more surface. Here, there's more molecules that are inside the middle of the droplet. So the fact that liquids form droplets or bead up on surfaces is because of surface area. And this is always true for all liquids. They all have surface tension, that there's this resistance to it, but some have more surface tension than others. So water is relatively high, and that's why it forms those big beads. Another example or implication, this is why like insects can stand on the surface of the liquid. Basically, right here, you can see there's like a depression where the foot of the insect is on the surface of the water, and it's pressing down. But in order to break the surface, right, for the bug to sink into the water, you'd have to break the surface, and that would lead to a really big increase in surface area. Here, you just kind of depress it a little bit, you kind of stretch the surface a little bit, but you don't break it. You don't have to make a bunch of new surface. So that's why little things will float on top of water. So like paper clips sink in water, but you can float a paper clip on top of water if you're careful when you put it on there, because that resistance of breaking the surface, you got to get into the water to sink. So it just doesn't even break apart the water molecules and enter into the water. So stronger intermolecular forces lead to higher surface tensions. And how we can think about this is at the surface, if you have, say, this is, a droplet, these are, say, not to scale size molecules, but this molecule that's, say, out on the surface, it is necessarily missing the other molecules over here with which it can form intermolecular forces. As a result, it has fewer intermolecular forces. That means it's in a relatively unstable situation. These water molecules that are, say, inside the droplet, they're surrounded by other molecules that they can form intermolecular forces with. They can interact with, whatever it may be, whatever type of force it is. And so moving in order to increase the surface, you have to take one of these molecules from the bulk, where it's surrounded by partners, and move it to the surface where it has fewer partners. And the stronger the intermolecular forces are on these molecules, the more resistant those molecules are going to be to moving out to the surface. They don't want to move to the surface. They want to stay inside the bulk. You can also see that because there's less, what ends up happening is that because you're missing these bonding partners out here, that what ends up happening is that these molecules are literally pulled in. Because there's kind of nothing holding them out. And so that's what pulls them in, kind of keeps the droplet small and maintains a smaller volume. Let's look at an example of making a prediction about surface tension. Which compound has a higher surface tension, H2O or H2S? Whenever we're dealing with these sorts of properties, liquid properties, especially surface tension, and we want to make a prediction about the relative values, we always want to think about, well, how does that property depend on intermolecular forces? We have H2O and H2S. We know they may have different intermolecular forces. How will that inform our surface tension? And strong intermolecular forces lead to high surface tensions. Molecules do not want to move to the surface. They want to stay in the bulk. So what are the primary intermolecular forces? We know that whichever one is stronger is going to have higher surface tension. So what are we looking at here? Which one's stronger? Well, if I want to know primary molecular forces, I need Lewis structures. So I've got H2O and I have H2S. We've looked at these molecules before. Water forms hydrogen bonds. We know that because of the OH covalent bond in the molecule. H2S is dipole-dipole. We know it's polar because it's an atom-centered molecule. You've got that sulfur in the middle with lone pairs on it. Hydrogen bonding is stronger than dipole-dipole interactions, so H2O has a higher surface tension. So we would expect one of the implications if you had if you spilled liquid water and liquid H2S on the same surface, the droplets of water will be tighter than the droplets of H2S. They're going to more flatten out. If our oceans or ponds were made of H2S, it would be more difficult for a bug to land on the surface because it has a lower surface tension. It's easier to break through that surface to spread it out. But water, thankfully, has a very high surface tension, which is important for a lot of things that depend on the fact that water likes to stay close to other water molecules. It's hard to break that surface. It's also why it hurts a lot when you land on water. So viscosity is another liquid property, which is the resistance of a liquid to flowing. So it's a little, it can be a little counterintuitive. Viscosity is resistance to flow. So high viscosity means the liquid does not flow very well. So words we use to associate with those liquids are like thick or gummy is the idea, whereas low viscosity would be a runny liquid. So water has a relatively low viscosity as far as liquids go. It can flow, whereas honey would be something that has a high viscosity. It doesn't flow very easily. It's very slow, right? When you turn on a tap for the sink, the water just starts to flow immediately. Gravity affects it. Whereas, you can kind of imagine there's a motion here that this is much slower that's coming down. And so we can see that idea. Another thing that this image shows us is if we think about surface tension, the fact that the honey, when it drips, it has this really long drip where it has this long attachment that doesn't break. That is because in order to break it, you'd have to form surface. That would be an increase in surface area. So there's an energetic cost to that. So that doesn't break, whereas you can see the water forms droplets along the way, indicative of the fact that it has a lower surface tension, so you can form droplets. But honey's really hard to form those droplets. You got to get it really, really stretched, and you'll note it eventually breaks once this is really narrow. So it's a smaller surface area forming. So high viscosity, again, corresponds to strong intermolecular forces. If we think about viscosity, it's the idea of flowing, and flowing means the molecules are moving relative to other molecules, which means they are separate. You're necessarily breaking intermolecular forces. And so water can form hydrogen bonds, so it has very strong intermolecular forces, but it can only form a handful of hydrogen bonds. Sucrose, this is sugar here. This is the primary ingredient in honey. It's water and sugar. And if you look at this sucrose molecule, there are a lot of OHs that are hanging off the side. Remember, this is like a condensed formula, so all these OHs hanging around all over the place. So one sugar molecule can form 8 hydrogen bonds with other molecules. And so that's a lot of hydrogen bonds, and that's why honey is more resistant to flowing, because it's much more likely that each and every single sucrose molecule is participating in multiple hydrogen bonds with other molecules. You get just this kind of big network of molecules that are all linked together. So that's why it's really slow to flow, because they're all kind of stuck together, lots of connections with each other. It's more of a network. And so if you think about water can form 2 hydrogen bonds, so that'd be like pulling apart 2 hairs if you try to break 2 hairs at the same time, whereas sucrose has 8. So, the more hairs you try to break at the same time, the harder it is. The more hydrogen bonds you're trying to break at the same time, the more difficult it is. Which compound has a higher viscosity? H2SE or H2TE? So if whenever we're looking at predicting liquid properties, and especially relating them to the compound itself, the formula, we want to think about how does that property depend on the intermolecular force, because that's what's really the factor in these compounds, is what intermolecular forces they have. And we know strong intermolecular forces mean high viscosity, high resistance to flow. So what are the primary intermolecular forces for these molecules? And which one's going to be stronger? And that means we need to draw the Lewis structures. So H2Se, H2Te, both selenium and tellurium are in group 6A. So we get 2 bonds and 2 lone pairs on each of them. If we look at these are both polar molecules. There's lone pairs on the central atom, meaning they're polar. Dipole, it's primary intermolecular force. So we have a tie. There's not one is stronger than the other, and we need to use dispersion. And stronger dispersion corresponds to a larger molecule. H2Te is a larger molecule. Tellurium is a much larger atom with more electrons than selenium, right? More electrons gives you more opportunities for those dipole fluctuations. And so since it has stronger dispersion, that means it has stronger intermolecular forces, and H2Te has a higher viscosity. So if you were to pour these two liquids, you would expect that H2Te would pour more slowly. You'd get the long drips, you'd get the slow flow. It'd be harder to mix if you tried to, stir it with like a spoon, all that kind of stuff. It has higher viscosity. See, told you. Would not have a participation question in every video. So nice little break maybe. See you in the next video.